So this will be our first lecture in the module on combinatorics or counting. So what is combinatorics? Well, combinatorics can be described as the art of counting. It's the study of techniques that will help us to count the number of objects in a set quickly. There are highly sophisticated results that can be obtained using simple concepts. And the following examples will illustrate the many questions concerned with counting. So for example, a snack bar serves 5 different sandwiches and 3 different beverages. How many different lunches can a person order? So one way of determining would be to list or enumerate all of the possibilities. And one systematic way of doing that is by means of a tree. Every path that begins at the position labeled start and goes to the right could be interpreted as a choice of 1 of 5 sandwiches followed by a choice of 1 of 3 beverages. So I'll show you the tree here. We have start, and then you have first a choice of 1 of 5 sandwiches, then a choice of 1 of 3 beverages, and then what you'll see here on the far right is your final selection. So the far right is the list of all the possibilities. You could have a bologna sandwich with milk, a bologna sandwich with coffee, a bologna sandwich with tea, a ham sandwich with milk, and so on. So if we needed to, say, write the set of all possible lunches, then we would have something like you see here: beef, milk, beef, juice, and so on. But perhaps a quicker method would be to just observe that there are 3 possible beverages, 5 possible sandwiches. So if you multiply 5 times 3, you get 15 different possibilities, and that's exactly what we found in our tree as well. So for each of the choices of sandwich, that branched off into 3 combinations of sandwich and beverage. So 3 times 5 gives us the total list of 15. We already know how to find the Cartesian product of 2 finite sets. And so we also discussed how the elements in the Cartesian product, that there would be the cardinality of A times the cardinality of B, many elements in the Cartesian product. So another example, a person is to complete a true-false questionnaire consisting of 10 questions. How many different ways are there to answer the questionnaire? Since each question can be answered in one of 2 ways, either true or false, then there are a total of 2 to the 10th power, because there are 10 questions. So 1,024 different ways to answer the true-false questionnaire. So if you tried to draw a tree diagram for the true-false questionnaire, your tree would end up having 1,024 different branches, so it becomes quickly unwieldy to actually enumerate or to list all of the possibilities. So this brings us to what is called the rule of products. If 2 operations must be performed, and if the first operation can be performed in, say, p sub 1 many different ways, the second operation could be performed in p sub 2 many different ways, then there are p sub 1 times p sub 2 different ways that the 2 operations could be performed. It's important here that this number p sub 2 for the second operation doesn't depend on the option that's chosen at first. So another way of saying that is that p sub 2 is independent of the first operation. If that's not the case, if p sub 2 is dependent on the first operation, then the rule of products cannot be applied. So let's revisit the lunches. Assume that coffee is not served with a beef or chicken sandwich. Then by looking back at our tree diagram, we could see that we could eliminate beef with coffee and chicken with coffee, and then we'd have only 13 different choices. But we can no longer apply this simple rule of 3 times 5. There's also an extension of this rule of products. if you have a sequence of operations consisting of more than 2 operations. It's going to work exactly the same way. If you have n different operations to perform, and for each of the n operations, you could have p sub 1, p sub 2, or p sub n ways of performing them, respectively, and all of these are independent operations, then you just multiply the number of different ways to complete the process in each step to get the total of number of different ways. So for example, a multiple choice questionnaire contains 4 questions that have 2 possible answers and 3 questions with 5 possible answers. Since the answer to each question is independent of the answers to the other questions, the extended rule of products would apply here. So we'd multiply, there are 2 ways to answer the first question, 2 ways to answer the second question, 2 ways to answer the third question, and 2 ways to answer the fourth question. Then there are 5 ways to answer the third question, 5 ways to answer this sixth question, and 5 ways to answer the 7th question. So you would get 2 to the power 4 times 5 to the power 3 many different ways, which is 2,000 different ways to answer this questionnaire. One last thing of interest here is that previously we introduced the notion of the power set, which is the set of all subsets of a given set. And we said that we could use the rule that the cardinality of the power set of a given set is 2 to the power n, where n is the cardinality of the set. So this works for finite sets. And this follows from this rule of products, because essentially to determine if an element is in a subset, there are 2 answers. Either it is in the subset or it is not in the subset. So you get 2 to the power n many different subsets. So the proof is here, if you want to go through that a little more in depth. Now we're ready to work on some exercises. So the first exercise says, in horse racing, to bet the, quote, daily double is to select the winners of the first 2 races of the day. You win only if both selections are correct. In terms of the number of horses that are entered in the first 2 races, how many different daily double bets could be made? So here it's not telling us the actual numbers. So we're going to do this sort of abstractly. We'll say, assume there are n horses in the first race of the day, and maybe m horses in the second race of the day. Then we know that we're going to use the rule of products here, and we'll say there are n times m daily double bets, let's say different daily double bets, that can be made. Because first you have to choose a horse for the first race, and you have n different choices. Afterward, you choose a horse for the second race, and you have m different choices. So you have n times m total choices. Next we have the Pi Mu Epsilon Mathematics Honorary Society of Outstanding University wishes to have a picture taken of its 6 officers. There will be 2 rows of 3 people. How many different ways can the 6 officers be arranged? So sometimes it's helpful to draw a little diagram, and oftentimes with counting problems, the diagram is going to be as simple as just sort of putting these little spaces here. So I'm thinking of these as places for the people to stand or places for the people to sit. And I put them in 2 rows because it says we will have 2 rows of 3 people. There are 6 people to choose from, and the question is, how many different ways can they be arranged? Well, if we think about these as 6 different processes, and say maybe this is the first process, and then this is the second, and so on. Finally, this is the 6th. Then for the first person, we can choose between 6 different people. We have 6 different people that could stand in this space. But once we've assigned someone to stand there, then for the second spot, we only have 5 choices of people. Then in the third spot, 4 choices of people, 3, 2, and 1. And it really didn't matter which order we assigned them in. I could have first said, this is the one I'm going to do. I would still have 6 choices for the first process, and then whatever I decided was the next spot, only 5 choices because I've already assigned someone. So now if we apply our rule of products, for the first process I had 6 ways, then for the second I had 5, then for the next I had 4, 3, 2, 1, and so on. There are, let's see, 6, 24, 120, 720 different ways that I could arrange the 6 officers. And when we're multiplying all of the numbers between 1 and a positive integer larger than 1, as we've done here, we can denote that with the exclamation point. So this will be read as 6 factorial. So if we see this notation, 6 exclamation point, it's just telling us to do 6 times 5 times 4 times 3 times 2 times 1, in this case 720. But I believe we'll see the factorial in a future lecture. Okay, a clothing manufacturer has put a mix and match collection of 2 blouses, 2 pairs of pants, a skirt, and a blazer. How many outfits can you make? So let's start by assuming we need one of everything. We have pants and skirts. So we would need a blouse and a pant and a blazer, or we would need a blouse and a skirt and a blazer. Since I have 2 blouses, I can think of this as I have 2 choices for my blouse, and then I have 2 pairs of pants, so I have 2 choices for my pants, and then I have 1 blazer. So this gives me a total of 4 choices if I do blouse, pant, and blazer. If I do blouse and then skirt and blazer, I have 2 choices for my blouse, and there's just 1 skirt and 1 blazer. So I have 2 different ways that I could do blouse, skirt, and blazer. So altogether, we're just going to add these up. There are 6 different outfits. Now, then the question asks, did you consider that the blazer is optional? And initially we did not. We said that we have to have a blazer. So if the blazer is optional, then we can think of that as another choice. So here we could have blouse and pant and blazer, Or we could have blouse and pant and no blazer. Blouse and skirt and blazer, or blouse, blouse and skirt and no blazer. And what this does is it doubles the possibilities. So in all, there will be 12 different outfits now. Okay, then the question says, how many outfits can you make if the manufacturer adds a sweater to the collection? So now we have 2 blouses, 2 pairs of pants, a skirt, and a blazer. So it's really the same question as with the blazer. Is it optional to wear the sweater or not? So if we must have a blouse, a pant, and a sweater, then it would still be 12 different choices. But if we make the sweater optional, like we did with the blazer, then there are 24. And this is a pant or a skirt, of course. If the sweater is optional, then again, it's another choice, so I multiply by 2 again. Next, suppose that each single character stored in a computer uses 8 bits. Then each character is represented by a different sequence of 8 zeros and ones called a bit pattern. How many different bit patterns are there? So for part A, I'm going to draw my diagram, and I'm going to say, here are my 8 bits. And in each place, I'm putting a 0 or a 1. So for each place, I have 2 choices. So I have 2 choices, 2 choices, 2 choices, meaning I have 2 to the 8, many possible different bit patterns, which is 256, 6 different bit patterns. Part B says how many bit patterns are palindromes, meaning the same backward as they are forward. So I'm going to have my first half of them because there's a total of 8. And then my second ones are going to match. So if I had, for example, 1, 1, 0, 0, then in order to be a palindrome, this would have to be 0, 0, 1, 1. That's just one example, right? Where if I read it forward or I read it backward, they're exactly the same. So what that tells me is that the second 4, which I've written in red, are completely determined by the choice of these first 4. So I really only have these 4 choices to make. So I have 2 to the 4, which is 16 different choices. And then once I've assigned them, I already know these. So it's just 16 different possibilities that are palindromes. And then finally, how many different bit patterns have an even number of ones? So again, I'm going to draw in my bits. 1, 2, 3, 4, 5, 6, 7, 8 of them. And I know that I could have an even number of ones. That could be I have 0 ones, or I could have 2 ones, or 4 ones, 6 ones, or 8 ones. So that's a lot of different options to explore. But there's actually an easier way to think about this, which is that I'm just going to go ahead and let myself choose the first 7 spaces. So that's 2 to the 7, 128 different choices. Once I've put them in place, I will look at the first 7 bits and I will decide, do I have an even number of ones? So place the first 7 bits. If there are an even number of ones, then the final bit will be a 0. And if there are an odd number of ones, then the final bit will be a 1, so that I get the even number that I wanted. And in doing this, I found all of the possibilities. So again, just by thinking about the problem, I was able to find that there are 128 different patterns, bit patterns, that have an even number of ones without actually having to count them all, which would have taken quite a while. All right, let's let A be the set 1, 2, 3, 4. First, let's determine the number of different subsets of A. So the number of different subsets of A is the cardinality of the power set of A. And we know that that's 2 to the cardinality of A, which in this case is 2 to the 4th, which is 16. Then we're asked, if A is 1, 2, 3, 4, and 5, determine the number of proper subsets of A. So in this case, the cardinality of the power set of A is 2 to the power 5, because this set A is 1, 2, 3, 4, 5. So that's 32 subsets of A, but this includes the set A itself. And the only subset of A which is not proper is the set itself. So let's just remove it from our count. Then the number of proper subsets will be 32 minus 1, or 31. Okay, now consider 3 persons, A, B, and C, who are to be seated in a row of 3 chairs. So let's draw my 3 chairs. It says, suppose that A and B are identical twins. How many seating arrangements of these persons can there be? A, if you're a total stranger. or B, if you're the twins' mother. So the idea here is whether or not we can tell the twins apart. If we're a total stranger and we can't tell the twins apart, then the question is really just a matter of which chair are you, the stranger, sitting in. So you could be sitting in this chair and the twins are here, or you could be sitting in the middle chair, one twin on either side, or you could be sitting in the third chair. And you can't tell the difference between these other two people, so it's really just these three possibilities. Whereas, if you are the mother of the twins, then hopefully you can tell your children apart. And so now there are three distinct people involved. You and your sons A and B. So now we have a process where there are three possibilities of who could sit in the first chair, then two possibilities of who would sit in the second chair, and just one possibility of who would sit in the last chair, for a total of 6 possible seating arrangements. I want to use the factorial notation again. This is 3 factorial, or 6 possible seating arrangements. So this problem is designed to show you that different people could have different correct answers to a question like this. Next, a questionnaire contains 6 questions, each having yes or no answers. For each yes response, there's a follow-up question with 4 possible responses. The question has asked us to draw a tree diagram to illustrate how many ways a single question can be answered. So we just have to do one question. We know that it's a yes or no question, so I would probably say this is the start, and I either answer yes or no. Then it says, for each yes response, there's a follow-up question with 4 possible responses. If I said no, then I don't have a follow-up question. So this is just, I stop here. If I say yes, then I get 4 choices for a follow-up question. And I'm going to call them A, B, C, and D, the 4 possible responses for the follow-up question. So this is the tree diagram for the number of different ways. So for each question, how many possibilities do I have? Well, I either answer no, or I answer yes and A, or yes and B, or yes and C, or yes and D. So there are a total of 5 possibilities. So 5 different ways to answer a single question. And then part B asks us, how many ways can the questionnaire be answered? And we were told that there are 6 questions in the questionnaire. And we found out there were 5 ways to answer each question. So there are 5 to the power 6 many ways to answer the questionnaire. If I think of each of the 6 questions as a blank, then I had 5 ways to answer the first one, the second one, the third one, and so on. And so in total, 5 to the power 6 is 15,625, I believe. And that looks like the conclusion of this introduction to counting. So we'll do more counting problems in the next lecture.